recording. Okay, so today's lesson is on higher order derivatives, which basically means you take derivatives of derivatives. If y equals f of x is some function with a derivative dy by dx equals f prime of x, the second derivative, let me make that a little skinnier, of the function is the derivative of the derivative. All right, notation-wise, this is what we look like. The second derivative is denoted by putting 2 primes here instead of 1. So that tells you that you've taken the derivative of the derivative. Another way you can do this is with Leibniz notation. So your first derivative is this thing, dy by dx, and then you're taking the derivative of that derivative. Now, if you're looking at this and it's like, why didn't they put a y here? Well, the reason they didn't put a y there is because once you've taken the derivative, it isn't the original y function anymore. X is still x because the variable, the input value of x is still the same for whatever point you're looking at, but the y value, the output is different. It's not the same thing anymore. You don't have this sheet? Okay, I'll get you one in a minute. Just wait till O Canada hits there. So when you look at this kind of put together, you'll notice that the squared has to go on the d, not the y, because you're repeating the process of the derivative, but you're actually only finding the change in y once, because once the y is changed, it's not the y function anymore. But the x is still the same, so you put a squared on the x. All right, so this is easier to do than it is to explain, so let's just do an example here. Find the second derivative if y is equal to x to the power of 6. So the first derivative is 6x to the 5. And the second derivative would then be to do the derivative process over again, which would be 30x to the 4. Okay. Let's see if I can just make a quick pause here. And we'll pause for O Canada. Okay, and we're recording again. All right, next. All right, what do we do with this one? We want to find two derivatives. We want to find the derivative of the derivative. So, first thing we'll find, actually the first thing we'll do is we'll change this into a form that allows us to find the derivative a little easier. We'll change the radical to a rational exponent. Now we'll find f prime of x, which is going to be 6x plus 1/2 x to the negative 1/2. Okay, now there's no point in simplifying at this point because I got to do the derivative again. So let's just do the derivative again and then we'll look at simplifying it. So the derivative of 6x is just 6, and for this one, you leave the coefficient that was already there. The exponent becomes your new coefficient, and then you subtract 1 from that exponent. Let's tidy that up a little. And it's going to look like, actually, let me change the sign there. A positive times a negative is a negative. And that would be negative 1/2 minus 1 is negative 3/2. Okay, now again, that's a perfectly good answer. But if the question did want this changed into not having negative exponents, you could, of course, make it look like this. Or again, what if we didn't want fractional exponents at all? Then we could change it into a radical form. And remember, x to the cube, or x to the power of 3/2 is like saying the square root of x cubed. So you could say that that's 4x root x. And you could even make it simpler from there. You could times top and bottom here by root x. And make it 6 minus root x. Oh, oops, hang on. Getting ahead of myself here. 6 minus root x over 4x squared. And if you wanted that as one expression, you could even say that it's 6x, or no, I guess it would be, hang on a sec. What would it be? Common denominator here would be 4x squared. So that would be 24x squared minus root x over 4x squared. There we go. All of these things do say the same thing. They're all just different versions of the same thing. Okay. Next, find the first 5 derivatives. All right, so one at a time. What's the first derivative? So the first derivative would be to change x to the power of 4 into 4x cubed plus 6x squared minus 10x plus 3, and remember the derivative of a constant is just 0. So there's the first derivative. The second derivative would be 12x squared plus 12x minus 10. The third derivative would be 24x plus 12. The fourth derivative would be just 24. And if you want a fifth derivative, remember the derivative of a constant is just 0. And notice the progression, right? You go from a cubic, or well, from a quartic to a cubic to a parabola to linear to a constant to 0 to nothing. And just to kind of show that progression, I actually did Desmos this one. So there's the original, right? It's definitely a quartic, right? It changes directions 1, 2, 3 times. And then its derivative is a cubic, which changes direction twice. And the derivative of that is a parabola. And then the derivative of that is linear. And the derivative of that is my constant. And the derivative of that is nothing. The x-axis. Okay, cool. All right, let me turn all these off. By the way, once it gets down to a constant, Desmos actually does figure it out for you, which is kind of nice. And just, oh, where's my cursor? There we are. Okay. All right, example 4. Now we're finally going to have to use our product law. Again, I think the first step I would do for this is to change this to x to the 1/2 times x plus 1. But the easiest way to deal with this now, I think, is to just use my product law. So f primed of x is going to be, okay, so it's the derivative of the first times the second plus the first times the derivative of the second. Now, because I have to do this again, I think I might do a little bit, this time I think I might do a little bit of simplifying first. Okay, I don't have to, right? There is more than one way to approach these. But I think I'm going to do a bit of simplifying before I run it through for my second derivative. So that's going to be x plus 1 all over, I guess I could say 2 root x plus root x. And since I have to do a derivative of this again, maybe I'll actually combine that into one thing so that I can just use my quotient law on it. Right? If it's one expression, I can just use quotient law. So I'm going to multiply top and bottom of this thing by root x over root x, or sorry, 2 root x over 2 root x, so that they have a common denominator. And that's going to be x plus 1 plus 2x, right? Because root x times 2 root x is 2x. all over, oh, this is supposed to be an x, not a 2. I don't know what I was writing there. All over 2 root x. So simplifying that again, I get 3x plus 1 over 2 root x. And then since I have to do the derivative of that, maybe I'll go switch back again to a fractional exponent. And now let's find the second derivative. Now that it's in a fairly easy form to work with, I can just work with this now as, oops, as a quotient law. So how does quotient law work? Well, it's the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. Okay, what does that tidy up to? Well, let's see, that is going to be, should have given you more room for this. If you have any loose leaf or something, you might need some loose leaf on this one. Okay, so that's going to simplify to, let's see, that is, remember that the goal at the end of this, I kind of forgot to mention here, is that we're actually finding a value this time. We want f prime primed of 2. So at some point we're going to actually plug a number in for x. We're going to plug in a 2. It's probably easier to work with radicals than fractional exponents when you're actually plugging in numbers. So I'm going to go to radicals. But let's tidy this up a bit first. 3 times 2x to the 1/2 is like saying 6 root x. Then over here, a half times 2, that just plain old cancels. And I'm going to get 3x plus 1 times x to the negative 1/2, which is like saying 3x plus 1 over square root of x. And when I square the denominator, I'm going to get 4x. Okay. All right. I could, if I wanted to, make this numerator here easier, or you know, by combining it. But since I'm plugging in a value, I might as well just plug in the value. So let's find f prime primed of 2, just from here. So that's going to be 6 root 2 minus 3 times 2 plus 1 over the square root of 2 all over 4 times 2. All right, tell you what, let's get you doing some thinking. Simplify this as much as you can from here. I'll give you a minute. And when I say simplify it, remember that in a radical expression, we don't want radicals in the denominator, and I'm actually going to tell you this will simplify down to something that would be a root b over c. So see if you can make it look like that. I'll give you a minute. I think you guys could probably use some practice with your radical skills. So let everybody try that for a minute. Okay? While you guys are practicing that, I'll take attendance here. No, that's not what I wanted to do. There we go. Sits there, nobody sits there. Oh, I think everybody's here. Right, 2 empty seats in the back, 1 empty seat in the front. Yep, everybody's here. Go. Okay. Back to that. All right, did you get there? So let's see, what should I do first? How about I'll just say that that's 6 root 2 minus, and let's make that 7 over root 2 and 8. All right, we need to combine this numerator into one single radical and one single expression that isn't a fraction. So I'm going to times this by root 2 over root 2. And that's going to give me 6 root 2 minus 7 root 2 over 2 over 8. Then I need a common denominator here of 2, so that's going to be 12 root 2 minus 7 root 2. Oops, hang on. That's a funny looking 2. Sorry, I'm thinking ahead to my next step. All over 2. And instead of dividing by 8, I'll times by 1/8, because again, I want a single non-complex fraction here. And that's going to be, what am I going to get? That's going to be 5 root 2 over 16, and that's the answer we were looking for. So there we go. No, we don't want decimals. Now, unfortunately, most graphing software, if we were using our graphing software, would give us decimals. Let's have a quick look at this. So let's see. If we had the original function, which was this thing, and its derivative is that, and let's say I didn't have an answer key and I wanted to know if the derivative that I had was, oh, wait a minute. Is this the right one? Oh, yeah, that's the right one. Let's say that I want to know that that first derivative is correct. Yep, it's exactly the same. So now let's try the second derivative. And there it is. The second derivative is there. And let's see if my answer for the second derivative, which I didn't bother simplifying, is correct. And yep, it is. And then run through the calculator, and you'll see that g prime primed of 2, or in this case, I guess it was f on your question, but the second derivative at the point where x is 2 is 0.4419, and if you actually run that through your calculator, yes, that is 5 root 2 divided by 16. So there we go. And there it is. Okay, so let me make all these go away. And one more. Let's do a graphing question. So think about what a derivative of a derivative means. Remember that a derivative is finding a slope, right? Think about it back when you learned this in the physics portion of grade 10 science, right? The slope on a distance time graph is velocity, and the slope on a velocity time graph is acceleration. So finding slopes of slopes isn't a new idea to you. So let's start with this guy. Easiest things to find first are the places where the tangent would have a slope of 0, which looks like it happens here, here, and here. Let me maybe make that a little smaller so you can see them both. And okay, so then underneath that, so it looks like at about 2.5, I have a 0. And then at, let's see, what is that? That's a half, 1.5, and a little bit. So a half, 1.5, and a little bit, I have a 0. And then somewhere at about 4.25, I have a 0. So somewhere about there. All right, what do I know about this thing? Well, I know that its slope is positive everywhere here, right? All these tangents are positive, and they start by being quite steep, but then as of course you get closer to the 0, they get less steep. So I start off very steep, and then I get less steep. So something like that. And actually, I don't like that line now that oops. Oh, I don't know what I just did. I hit the wrong thing. There we go. And let me try that line again. So I know it's going to be steep, and then less steep, and then it's going to, now, how far down does it go? Well, actually, from here to here, notice the slopes don't get very steep. In fact, I actually kind of like to figure out what the slope is when x is 0. When x is 0, it looks to me like the slope is, I don't know, like from here to here, I can kind of estimate to be a straight line. And that has a rise of a half, 1.5 over 1. So 1.5 over 1 is about 1.5. So I think this is going to go down to about -1.5. So I don't know, maybe down about there. and then it's going to go up again, right? Because starting, it goes back to 0. And then it's positive from here to here. But again, it's not going to get very high. I mean, the slope here, say that you approximate from here to here as approximately a straight line. That's about a slope of about a half. So it's only going to maybe go like that. Then afterwards it gets negative and it kind of sharply goes away. So I think it's going to be something like that. Quick check, I went from a power of 4 graph, a quartic, to a cubic. Seems pretty reasonable. Okay, I'm actually not a big fan of the way I did that loop in there, but good enough. All right, now let's find the derivative of the derivative. So somewhere in here, I think it might even be about -1, I have once again a tangent of 0. So at -1, I'm going to have, or around -1, I'm going to have an x-intercept. And then I'm going to have a tangent of 0 here. Looks like it happens pretty much right at 3. And this was a cubic, so this thing, of course, has to be a quadratic. And quadratics have symmetry. I know that the vertex of my quadratic is going to be exactly halfway between the two x-intercepts. So where is halfway between -1 and 3? Well, that would be +1. So what approximately is my slope here at -1? Well, again, it looks to me like I have a rise of 1, 2, or a half, 1, and a run of a half, 1. It actually looks pretty close to being like +1, like just a little bit less maybe than +1. So I'm going to guess that my vertex is right maybe just under +1. And then, of course, it is a parabola, so it's kind of a wide parabola. But there we go. I think that is very nicely estimated. And on the test, that's all we're going to ask you to do. It only has to be an estimate. You just have to get the general shape correctly. And that's basically what we're looking for. Okay? And just to see how close we are, I kind of estimated what this graph is. I wasn't given an equation for this graph. But if I know its x-intercepts, right? This x-intercept is -4, so that means x plus 4 is a factor. This x-intercept is a half, so x minus a half is a factor. This x-intercept is 3, so x minus 3 is a factor. And this x-intercept is 5, so x minus 5 is a factor. There is an a of some sort that I don't know, but I actually can read the y-intercept. The y-intercept happens at 0, 1/2. So I know that y is 1/2 when all of these x's are 0. So I came up with a quick calculation on that and found out that, what did I find out? That's going to be a negative. And 4 times a half is 2. 2 times 3 is 6. 6 times 5 is 30. Divide both sides of the equation by -30. And there we go. That's my a value. So this a value is -1/60. So then I went to Desmos and plugged all that in. And let's see. So I came up with that equation. And that's pretty close. That's pretty much the same graph that is, right? Close enough anyway. All right, now let's see how good my estimations are. This is there's my first derivative. Let's see, let's compare it. How good was my first derivative? A little wonky, but the same basic shape. And that's really, at the end of the day, all I care about. And what's the second derivative? A parabola that goes to not quite 1 and has x-intercepts. Now my x-intercepts are off just a little, not much, but just a little. But again, compare that to this, and I'd say very much close enough. Okay? All right. That's all that we're doing for a lesson, so I'll stop the recording.